Hi everyone, my name is Yuan Kai. I'm a postdoc at Fudan University now, and I will be presenting our paper GAR, a Generate and Rank approach for natural language to SQL translation. Okay, so let's start with what is natural language to SQL problem first of all. So here is an example from the public benchmark Spider. And the problem is actually very straightforward, which means we are going to take an NL query along with the corresponding database schema, and we are going to translate it to the SQL query that can be executed by the database, then maybe get the result. So this is the whole picture of the natural language to SQL problem. And next thing we need to talk about is how to tackle the NL to SQL problem in existing approaches. With the advanced in neural machine translation techniques, the mainstream approaches generally formulate the NL to SQL problem as a language translation task, and will use the sequence-to-sequence framework to build the models. Okay, as you can see here, the encoder receives the given NL query as input, and depends on different model designs, the database schema will also be encoded properly, either by an actual encoder or shared the same one as the NL query. And next, on the other hand, the decoder is used to output the SQL tokens in sequence, and the decoder considers both the representations or the features from the NL queries and the database schemas to output properly. Usually, in order to have a good understanding of natural language semantics, current approaches prefer to incorporate a pre-trained language model under the sequence-to-sequence framework to get a better word representations. While the existing approaches have received significant improvements over the public benchmarks, those approaches still have some problems. And we observe that most erroneous translations happen with complex queries. The tables here list the detailed result of the two state-of-the-art translation models, which shows that the performance drops when the query becomes harder. The reason here we believe is that the harder queries need a deeper understanding over the databases, while only leveraging the language models to understand is very limited. So the goal of GAR is to employ the database semantics to further improve the overall performance. In order to have the database semantics enhanced, GAR assumes a set of sample queries are given, and instead of following traditional sequence paralleling, GAR is implemented in another way, which using the following three steps: the generalization first, the SQL2NL natural language second, and learning-to-rank last. Okay, so let's go through the GAR step by step in the next couple of slides. So the first one is the generalization. To maximize the semantics the given sample queries have, we are going to generalize the sample queries by using a decompose then recompose approach. As illustrated here, the decompose means to crack the sample queries each by each into a set of small units, where the units represent different semantics over the underlying database. And then the recompose means to random combine those unit and to generalize to a broader coverage of possible queries. So if you look at the paper, you will notice that we're actually using the parser trees to represent the sample queries and the generalized queries. But for presentation, we use a better visualization way to present the whole process for the audience. After having the generalized SQL queries, next thing we are going to do is to map the SQL semantics back to the natural language semantics space. We think comparing the semantics in two modalities is not very easy, so mapping into the same one will be a good option for us. So we choose the SQL2 natural language, which is a reverse process of natural language to SQL, and uses to interpret the SQL semantics. And yes, there will also have many machine learning based approaches to achieve the process, but to ensure as much semantics as possible is preserved, we use a traditional but effective template-based approaches to do the job. And as you can see, we have predefined several templates, and we put each SQL part into each slot of the template and construct into the final sentences accordingly. Because the template is human designed, so the sentences may not be very natural, so we call the natural language expression as dialect in our paper. In addition, we also have some discussions about the importance of the SQL semantics of natural language to SQL problem. And we think the join operations may often raise the level of abstractions of queries, which may lead to the erroneous translations happened in the current approaches. And we further formulate the join semantics into 4 aspects: the join table, the join condition, the join description, and the table keys. And we're trying to incorporate the join semantics into the SQL2 natural language process to further enhance the overall performance. So here is an example to illustrate the point. So you can imagine that without the join semantics, the dialect generated by the SQL2 natural language process may not able to capture the specific semantics of the database, and we were not able to understand what the meaning of joining the flight and the airport tables using the airport code and the destination airport keys. But by incorporating the join semantics here, we can get a pretty good dialect to capture the specific semantics over the join operation. So this is very good for the next ranking purpose. After having the generalized SQL queries and the corresponding dialect expressions, the final step is to rank based on semantic similarity between the given natural language query and each of the dialect expressions. So we, in our work, we choose to use a learning-to-rank method to implement a 2-stage ranking pipeline to achieve the goal. For the first stage, we use a coarse-grained retrieval model to fast fill out most of irrelevant dialects in the first place, and then we use a fine-grained re-ranking models for accurate ranking, and hence to get the final result. Okay, the evaluation. We did an extensive experiments to study GAR in our paper. We choose 3 public benchmarks of natural language to SQL problem, and we also conduct a new dataset QBAN to for evaluating the importance of joint semantics particularly. And for the matrix, the first 2 matrices are used in most of the previous work, and we also add the second matrix for the ranking evaluation. Okay, baselines. We choose to use 4 state-of-art translation models to compare with GAR in our experiment, and all the baselines are based on the sequence-to-sequence translation model. And in addition, I would like to mention the sample query selection setting in our experiment. Since there is no sample query provided in public benchmarks, so we choose to use their validation or test set to generalize and then rule out all the ground truth queries and use the remaining set as the sample queries. So here is the main results of our experiment in the paper. So as you can see, GAR can receive better performance over the existing benchmarks, and also have a good response time over the different type of the SQL queries. And for the ranking purpose, the GAR can find the ground truth queries in most of the cases, which demonstrates its effectiveness of the current ranking models. Okay, just wrap up 2 main takeaways from the talk. The first one is the sample queries can bring database semantics for the models. So the models can have a better understanding over the underlying databases by using the given sample queries. So we think the natural language to SQL problem may not always be zero-shot, and actually in practice it is the case. So we think study the problem in future setting may also be an option. And the second one is the sequence-to-sequence framework is not the only option for natural language to SQL problem. The generate and rank approach is an alternative.